So next we're going to ask the same question again. What is the value of the parameter for the constant model that minimizes our mean squared error? So we're going to try and answer that question from a different perspective. Instead of using calculus, we're going to do some simple algebraic manipulations to arrive at the same answer. And they may seem a little bit arbitrary to you, but the reason we will follow through with them is because they are actually quite common in statistical manipulations, and they're often needed to obtain important results. And so it's important that you become familiar with these kinds of procedures, and they do highlight important concepts and relationships between our ideas, even though the actual algebra may seem to be a little bit like, oh, why are you doing that? There's actually good reasons for it. So let's dive a little bit into it. Again, like before, the algebra is all is described in detail in the slides. So the purpose of this is just to walk you through it and do the construction. But first, we're going to rely on two simple results before we dive into the answer, or one result and one definition, rather. First, we're going to use the fact that in general, for any set of data points, this quantity is equal to 0. The sum of deviations from the mean is equal to 0. You can see that this very, very easily by simply expanding these and realizing that this is more or less the definition of mean. So if we take this sum, right, this right here is equal to n times y bar, because y bar the mean doesn't depend on the index, it's a constant, and so we simply have n copies of it. These are all sums from 1 to n as always, and then the term on the left in here is equal almost to the mean if I put a 1 over n in front of it, which I need to compensate for. So because this was already almost the very definition of mean. So if I multiply and divide by n, this right here is the mean. And now I have that the first term is n y bar minus n y bar equal to 0. Okay, so this checks out pretty easily. The sum of deviations around the mean is always equal to 0. The mean is precisely the value that does that job. It is in the middle of your values, such that all of those differences add up to exactly 0. And the second one is simply the definition that I want you to remember of the sample variance, which is equal to from 1 to n of y sub I minus y mean squared. So we're going to use these two results. This is sample variance. Okay, so with these two little results in mind, or one simple result and one definition, we're going to take a look again at our definition of the mean squared error, our old friend. Right, and we're going to ask, how do we minimize this quantity? Well, what we're going to do is we're going to rewrite this expression in the following way. We're going to rewrite r of theta as y sub I minus theta squared. And the way I'm going to rewrite it is by subtracting and adding y bar. I haven't done anything. Obviously, that expression, I'm just adding 0, literally. So in principle, it seems like a silly thing to do. But by writing it in this way, I can regroup my terms and think of this as a sum of two quantities whose square I'm then going to expand. And again, this may seem a little bit pulled out of a hat. I can't exactly tell you how people came to it, but it's a very, very common kind of trick that I've seen it many, many, many times in statistics and physics and many other areas, and it's useful to get used to these kinds of manipulations. Sometimes it is very handy to rewrite things of this nature in a different way, to be able to take advantage of other identities and relationships. So if we write the empirical risk in this fashion, we now have that this is equal to, I'm going to expand this square, so square of the first term, switch to eraser by accident. Square of the first term is y sub I minus y bar squared plus 2 times the product of the two plus the square of the second, which is y bar minus theta squared. Okay? And so now we can distribute these sums, and what happens? We have the first term is 1 over n times the sum of y sub I minus y bar squared. And the second one, we have plus 2 over n, y bar minus theta comes out of the sum because it doesn't depend on the summation index, and we have sum over y over I of yi minus, minus y bar. But remember, result number 1 up here, this was exactly the quantity that we said was equal to 0. So this quantity right here is 0, and so it makes all of this go away. And then finally we have 1 over n, and times this the summation of those terms that don't depend on I. So what we have is n times y bar minus theta squared, because that summation, because y bar minus theta doesn't depend on I, so we just get n copies of it, and these n's cancel out. And finally, if you notice, this first term was our definition right here of sigma squared, right? So this was sigma squared. So what we have is that our empirical risk is equal to the sample variance plus second term vanishes, and the third term is y bar minus theta squared. And now the question is, when is this minimized as a function of theta? Right, that's the question we're trying to ask. Well, sigma squared is not a function of theta at all, so it doesn't play a role in that minimization. And y bar minus theta is a square. It's a positive quantity by definition, by construction. So the only way that it can be minimized is by being as close to 0 as possible. It can't be negative. And so since the only parameter that we can vary here is theta, the way to make this value right here as small as possible is to make theta equal to y bar. And that is the value that minimizes that term, because it will make, if theta is equal to y bar, if theta is equal to the mean, then the mean squared error evaluated at theta hat is equal to sigma squared. And this is part of the value of doing this little derivation, which is that we see two things. First, we found this result without resorting to calculus. You could argue that at the very end, you can take derivatives and show that indeed that's the answer, but basically we can just eyeball that on simple algebraic arguments about it being a square. But importantly, it also tells us that the value of the mean squared error at that point is reduced to the sample variance. And it's interesting, and this particular expression right here is interesting in that it shows us that the mean squared error can be decomposed into the sample variance plus something else, this additional deviation from the mean, which tells us that for that model, basically the sample variance is a floor. We can't do better than the sample variance. That's the least minimum squared error that we can get. And then beyond that, we get this extra contribution. And if we want the minimum possible value, we try to make that extra contribution, which is the deviation from the mean, be equal to 0 by picking the mean. So this second way of obtaining the same answer does give us some extra insight, in addition to showing us some algebraic tricks that are actually handy in a lot of statistical manipulations, and so they're worth learning.